Hi there, welcome to this Elkchemist chemistry video looking at Le Chatelier's principle. The aims of this video are to explain exactly what Le Chatelier's principle actually is, and then also to explain how we can apply Le Chatelier's principle to equilibrium reactions to make predictions about whether changing environmental conditions around that equilibrium system will cause the position of equilibrium to shift to the left-hand side or the right-hand side, and therefore favour the increased production of reactant or product molecules. Le Chatelier's principle dates back to 1884 and can be attributed to the French scientist and engineer Henri-Louis Le Chatelier. And it's a principle based on observations of dynamic equilibrium reactions and their behaviours as conditions are changed around them. What Le Chatelier very astutely recognised is that chemical systems at dynamic equilibrium were able to shift or move their positions of equilibrium to oppose or minimize any imposed changes in their external conditions. What that means is, if for example there was an increase of temperature on a reaction system at dynamic equilibrium, the dynamic equilibrium system responded to that increase in temperature and moved its position of equilibrium, moved its equilibrium position in a direction which allowed it to take in heat energy from its surroundings to a greater extent to bring down the temperature and minimize or oppose the imposed increase in temperature the reaction system was experiencing. Now, it turns out an ability to apply Le Chatelier's principle is much more vital than we might have realized. Many dynamic equilibrium reactions actually produce very useful products. So at an industrial level, if we can tweak and manipulate the conditions around a dynamic equilibrium to maximize the yield of product, this could be crucially and vitally important to human society, to maximize our profits from those processes, but also to produce these useful products on a large scale to meet the ever-increasing demand of our ever-increasing population. So what we have here is a good example of an industrial scale dynamic equilibrium reaction. This is the process for the production of methanol. Now, methanol is an alcohol and it is a useful feedstock chemical in multiple organic synthesis reactions. And it's produced by reacting carbon monoxide gas with hydrogen gas under specific temperature and pressure conditions. Now, in these sorts of questions, they will always tell you the energetics, the enthalpy change of the forward reaction. They won't necessarily tell you it's the forward reaction. Whenever they give you an enthalpy change of a reaction, it's referring invariably to the forward direction of the reaction itself. So this one has an enthalpy change per mole of minus 91 kilojoules. So that's telling us it's an exothermic reaction. If it's a negative enthalpy change, it means it's giving out heat energy to its surroundings and it is exothermic in nature. It's going to therefore drive up temperatures as the reaction takes place. Keep that in mind for later. The other piece of information they've given me in the question is the balanced equation, which gives me the molar ratio of reactants to products. What you can see here is 1 mole of carbon monoxide molecules reacting with 2 moles of hydrogen molecules to form 1 mole of gaseous methanol molecules. Now this is important because technically the left-hand side of the reaction is able to exert a greater amount of pressure comparative to the right-hand side of the equation. Why is that? Well, there are 3 moles of gaseous molecules on the left-hand side relating to the reactants. If there are more moles of gas molecules present, they will exert a greater pressure because pressure is force over area. A greater number of reactant molecules colliding with the surface area of the reaction vessel will generate more force and therefore a higher relative pressure. On the other hand, the right-hand side of the reaction, where the methanol is being produced, only forms 1 mole of gaseous molecules. Therefore, there's less moles of gas molecules present. Therefore, they're going to be colliding less frequently with the surface area of the reaction vessel itself, exerting less force and producing lower relative pressures comparative to the pressures that could be exerted by the reactants, which have more moles of gaseous molecules present. Again, keep this idea in mind for later when we talk about the influence of pressure on the dynamic equilibrium situation. Now, finally, we're in a position to start making some predictions based on our knowledge and application of Le Chatelier's principle. we're going to try and predict in which direction the position of equilibrium will move or shift if we change an environmental condition. In this case, we're going to talk about temperature. If I were to increase the environmental temperature that this reaction was exposed to, how would the equilibrium system respond according to Le Chatelier's principle to minimize or oppose that environmental condition change? Effectively, what I'm saying there is, what is the opposite of high temperature? Well, the opposite of high temperature is lowering temperature. So you've got to question yourself and ask, which direction of reaction would be able to bring the temperature down? Well, if we know that the forward reaction is exothermic and gives out the energy and would raise the temperature, it stands to reason that the reverse reaction, or the backwards direction reaction, would have the opposite energetics, would be an endothermic process and would be taking in heat energy from the surroundings. This would be lowering the temperature, and that would be the opposite of the imposed condition of temperature that we as a scientist had imposed upon this reaction condition. So that's exactly what happens, and that is exactly how we apply Le Chatelier's principle. So, to summarize, if we were to increase the temperature applied to this particular equilibrium reaction, we would find that according to Le Chatelier's principle, increasing temperature would cause the position of equilibrium to move or shift to the left-hand side in the direction of the endothermic reverse reaction. That's because this direction of reaction would be taking in heat energy from the surroundings and therefore opposing and minimizing the imposed increase in temperature we had applied. Now that would mean that the reaction would be moving, presumably we're moving to the left-hand side, okay? That's going to have the effect of increasing the yield of reactants and therefore would actually end up decreasing the yield of methanol as the position of equilibrium shifted or moved to the left-hand side. Now that would be not particularly favourable if our aim was to produce methanol, so it might not be the best condition to apply because it wouldn't necessarily increase the amount of methanol we'd be producing. Now, if we were to lower the temperature applied to this reaction system, according to Le Chatelier's principle, decreasing temperature would cause the position of equilibrium to move or shift to the right-hand side, and that would be in the direction of the exothermic reaction. Now, why would that be the case? Well, that's because the forward direction, the exothermic reaction, would be giving out heat energy to the surroundings. That would therefore be opposing and minimizing the imposed condition applied, the imposed decrease in temperature we were applying externally. And that's exactly what Le Chatelier's principle states. It's an opposition or minimalization of change theory. If we make the temperature low, the reaction system will respond and try to raise the temperature by moving the position of equilibrium in the suitable direction. Now, would that be the right move if we were trying to produce more methanol? Well, I think from an equilibrium standpoint, yes, it would. Because if we had caused the position of equilibrium to shift to the right-hand side, then that would cause the yield of methanol to increase. And from an economic standpoint, that's exactly what we were aiming to do. Methanol is the useful product, and we want to produce as much of it as possible. Therefore, being able to move the equilibrium position to the right-hand side and produce more methanol would be advantageous. However, with industrial equilibrium reactions like this one, there are other considerations to be made. Lowering the temperature would also have an effect on the rate of reaction. Lower temperatures mean less kinetic energy. This would decrease the frequency of collisions per second and also decrease the energy upon collision. And that would mean proportionately a smaller number of molecules would be colliding with energy exceeding the required activation energy. And this may actually be a problem. A really, really slow rate of reaction may compromise the production of methanol. You're getting a good yield of methanol from an equilibrium standpoint, but it's being made so incredibly slowly that it is no longer economically viable to continue. So what we need to do is select a compromise condition, a low enough temperature that the position of equilibrium is shifted suitably to the right-hand side, but not so low that the rate of reaction is incredibly slow and makes the reaction not viable. So a compromise condition would be a low enough temperature to make sure we get a good yield of methanol, but suitably quickly enough, so not too low a temperature. Okay, now let's look at pressure as a different external condition we can impose. If we were to increase the pressure on this particular dynamic equilibrium reaction, how would the reaction respond according to Le Chatelier's principle? Effectively, what is the opposite of increasing pressure? Well, the opposite of increasing pressure would be to decrease the pressure. My question is, to which side of the reaction we want to move the position of equilibrium to result in a lowered pressure? We want to move it to the side that has less moles of gaseous molecules because they will be exerting less pressure on the reaction vessel's walls. So it would appear to me that the side of the reaction that has less moles of gaseous molecules would be the right-hand side, i.e. the methanol product side. So to summarize once again, increasing pressure on this reaction system, according to the Chatelier's principle, if we did increase this pressure, it would cause the position of equilibrium to move to the right-hand side, towards the side of the reaction that happened to have the least moles of gaseous molecules present, which in this case is the product side, as this would help to oppose the imposed increase in pressure. By moving the position of equilibrium to the right-hand side, to the side with the fewest moles of gaseous molecules, we would be decreasing the pressure once again, which would be opposing the applied increase in pressure. Now, would that be useful to us from a production of methanol point of view? Well, yes, it would, because we would be increasing the amount of methanol being produced if the equilibrium had shifted to the right-hand side. And that is exactly what we want to do. We want to increase the yield of methanol. So applying a high pressure would appear to be a useful condition to help produce as much methanol as possible. Again, as before, there are limitations here. High pressure vessels are expensive and can be dangerous to maintain, so there have to be other economic considerations going on. But from a equilibrium stance point, increasing pressure would help to shift the position of equilibrium to the right-hand side and produce a greater yield of methanol. And then vice versa, decreasing pressure, according to Le Chatelier's principle, if we decrease the pressure, the position of equilibrium would move to the left-hand side because that's the side with the greatest moles of gaseous molecules. That would therefore cause an increase in pressure, and this increase in pressure would directly oppose and minimize the imposed decrease in pressure. So if we were to lower the pressure, the position of equilibrium would move or shift to the left-hand side, to the side with the greatest number of moles of gaseous molecules, as that would help to push the pressure back up and minimize or oppose the change in condition. Would that be useful from a production of methanol point of view? Not really, because if the equilibrium shifted left, we're going to be producing less methanol. This would decrease the yield of methanol, would be the least useful thing to have done from a production of methanol point of view. Just before I finish up and talk about how catalysts affect the position of an equilibrium, just wanted to say that if you find this video or other videos on the channel useful, insightful, helpful your learning with chemistry, please do think about giving this video a like, maybe subscribing to the channel, or even ringing the bell to keep notified of our ongoing content. As always, your support is hugely appreciated and helps to drive me forward. I'm trying to produce videos on a weekly basis if possible, and the more support I get, the easier that process becomes, so thank you very much in advance. So hopefully you remember that catalysts increase the rate of chemical reactions without being changed permanently themselves by the chemical process, and they do this by providing an alternative reaction pathway which itself has a lowered activation energy. Now, when it comes to equilibrium reactions, it turns out that catalysts do not actually affect the position of equilibrium and therefore don't change the yield of product. And that's because whilst they do increase the rate of chemical reactions, they increase the rate of the forward reaction and the reverse reaction in this reversible reaction by equal amounts. So ultimately, it's as if they had no effect on the actual position of the equilibrium, because the forward reaction is getting faster, but so is the reverse reaction to the exact same extent. So the reason why catalysts are used in dynamic equilibrium industrial processes is because they help to get the reaction up to equilibrium as quickly and as effectively as possible. That's the main role of the catalyst in that process. But once that's happened, they do not affect the position of equilibrium because they increase the rate of the forward and the reverse reactions by the same amount, by an equal amount. So that ends this tutorial on how to apply the Chatelier's principle to specific dynamic equilibrium industrial reactions. And hopefully you've realized that it's all about that opposition of change principle. That whatever condition you impose upon the reaction system, it will move its position of equilibrium to oppose and do the exact opposite. So if you raise the temperature, the equilibrium reaction will move its position of equilibrium to lower the temperature, whatever way that is. If you lower the temperature, then the reaction system will move its position of equilibrium to the side which will raise the temperature again, i.e. the exothermic direction. If you increase the pressure, then the reaction system will move the position of equilibrium to the side of the reaction which has less moles of gas. And if you lower the pressure, then the reaction system will move its position of equilibrium to the side with the most moles of gas to oppose that conditional change that you imposed. If you can get that opposition of change idea cemented down, then you will never get that prediction wrong. I hope that was helpful. Really great talking to you, and I'll see you on the next video. Thank you very much.